Thanks for the invitation, thanks for the introduction, it's great to be here. So I'm going to be talking about some work that I did with Rahul Krishnan. That's a picture of him up there. He really did, all the work, so you should remember his face, not mine. That's the other reason my face isn't up there, and also because I'm up here. Basically, at a high level, what we'd like to be able to do is fit these really cool deep generative models to text data, and we're going to figure out how to do that and why. So, a little bit of background on variational autoencoders, or deep latent Gaussian models. Basically, these are these cool deep generative models people have been talking about, where the generative process is you start with some Gaussian noise at the bottom, on the left there, pump it through some nonlinear function, which is parameterized as a neural network, throw a little bit more noise on there in some simple, typically factorized noise model, and that's how we say we get our observations. And then there's this neat trick that goes back to Helmholtz machines, but was recently sort of rediscovered, of rather than doing variational inference the way that I learned to do variational inference, which is to solve an optimization problem. Instead, what people typically do is train a neural network to figure out what are good parameters to a variational distribution that are going to do a good job of approximating the posterior distribution of our latent variables given our observations. Okay, so far so good. So, these models are great, but they're almost exclusively applied to images and not text or other high-dimensional, sparse, heavy-tailed data. There's a couple of exceptions to this, but they're exceptions. There are lots of papers about applying these to images, not so many for text. And why should that be? Given that sparse, texty kind of data is really everywhere. That arguably, maybe not by bits, but by maybe number of files, most of the files in the world, I would say, contain texty data. So why aren't we using these kind of models to fit this kind of data? Well, the answer is because if you have tried, kind of the naive thing, it doesn't usually work that well. So our hypothesis is that this is basically a local Optima problem. The issue, we hypothesize, is that there are lots of these rare words that we only observe maybe a few times in the corpus, and to learn how to but there are lots of those rare words. So the inference network, to figure out how to interpret those rare words and what should be how they should relate to posterior distribution, need to see those words a few times to figure out what to do with them, right? But the problem is that until they have done that, the gradient signals that the inference network is basically sending to the generative model are going to be terrible. They're going to be total garbage. And so we're going to be pushing the generative network in some basically totally random direction, random, both high variance and biased, whatever bias means in this context. And we're going to basically get stuck in a terrible local optimum. And that's our hypothesis. So to address that, what we do, the main idea is, which was also sort of independently had and presented at this conference, at the main conference a couple days ago, is rather than taking the variational parameters that the inference network gives us as the final word on how we approximate the posterior, instead what we're going to do is apply this secondary iterative optimization to improve those variational parameters, come up with a better approximation to the posterior, get a better signal that we can use to train our generative network, so that from the first iterations we're getting reasonable gradient signals for a generative model, even though our inference network hasn't really figured out what to do yet. There's one other little tweak that isn't sort of theoretically exciting, but it does help and it's easy to do, so you should do it, which is to, rather than feeding back and forth features to the inference network, it likes to get the IDF features better. So just, if you're going to do this, do that. So I won't bore you with a bunch of numbers about experimental results. Suffice it to say that there are some high-level takeaways. You can see them on the poster if you're interested in more details, or in the extended abstract. Basically, no big surprise. If you look at held out likelihood, deeper models do better than shallow models. It's 2016. We should all not be surprised by that, at least on large data sets. TF-IDF often helps, never hurts. You should use it. It's easy. The secondary optimization procedure, when applied at training time, always helps, especially for the deeper models. Actually, secondary optimization at test time is also very important. So that is to say that if you look at held out likelihoods, or held out bounds, I should say, that you get if you just use the parameters that your inference network gives you, there's plenty of room for improvement in those bounds, even after we've trained the model for quite a while. So that suggests that there's something difficult about using these neural networks to parameterize these posteriors for these kinds of models on this kind of data in our experiments. I'm trying not to be too general here, but there's something going on there. So, with that, I'll just say, great, we've got these techniques. They can allow us to fit these models of data. Now what do we want to do with them? Well, one natural thing to do with sort of bag of words models, right, is you might want to interpret them. You might want to summarize your data set somehow. There's been plenty of work on models that promise to do that and deliver on that promise, especially latent Dirichlet allocation is kind of the canonical example. So we kind of asked, what is it that makes these shallow models like LDA interpretable? One hypothesis is it's the linearity of the relationship that the model hypothesizes between our latent variables, our per document latent variables, and the word counts that we observe, right? So in a model like LDA, ordinarily in LDA, what I'm calling theta would be called beta, and what I'm calling z would be called theta, but I'm going to be consistent with my notation in this talk. One way to think about that, right, is that if I make topic 3 a little bigger, I can just read off the parameters how much more I should expect to see of any particular word, right? We can sort of frame that in calculus terms and say that, and say that the Jacobian of the expected observation vector with respect to the latent variable is something that you can just directly read off of the parameter matrix for a model like LDA, or a factor analysis model. So once you sort of look at it that way, right, I mean, Jacobians of expectations are easy enough to compute using automatic differentiation. That's what deep learning is all about. There's one little wrinkle, which is that for nonlinear models like DLGMs, this Jacobian depends on Z. And so rather than just being able to take it once, we have to average over samples of Z if we want a summary of the whole data set. And we played around a little bit with sort of, maybe the probabilities themselves are the right thing to work with, maybe the log probabilities are the right thing to work with. It depends a little bit on the application, but that's the basic idea. So one thing that Jacobian vector Jacobian matrix gives us is a tool for actually just diagnosing the learning process. So one thing we can do is just compute the singular value spectrum of that Jacobian matrix. And that's going to tell us basically how many, one thing that can tell us is how many latent dimensions are being used, right? So if there is some direction in latent variable space where if you move in that direction, it doesn't affect the expected observations at all, that basically means that the model has decided not to use that dimension. This is this variational pruning phenomenon that, that lots of people have observed in lots of models. And we find it here in spades. So what these plots are showing is the red and blue lines are the singular value spectra when we fit a shallow model, a model with no nonlinear hidden layers or anything like that. And we see this very nice, gently decaying singular value spectrum. The green line is what happens if you try and fit a model with 2 hidden layers and don't do this secondary optimization thing. And we see that we're able to fit 10, 15 latent dimensions, and that's it. Right, so we gave the model the opportunity to fit 100, to use 100 latent dimensions, and it's decided, no thanks, I'm good with 10. But when we do this secondary optimization, we find that the model is managing to use many more of the latent dimensions that we gave it to work with, which is great, which is exactly the sort of thing that we were hoping to see. And that translates to, greater expressive power, and it also translates to a more nuanced picture of, more nuanced representation of a given document. So that's interesting, but you know, let's actually. I said I was going to say something about interpretation, so let's do that. Another thing you can do with this Jacobian matrix is use its rows as word embedding vectors, right? So basically, it's saying, on average, how much each element of that vector is going to say for this word, on average, how much of an impact does modifying a particular latent dimension affect the likelihood of that word. As opposed to using something like word2vec, which is an inherently sequential model, or any of the other many fantastic word embedding models that have been proposed, we can actually get word embeddings from a deep bag of words model that actually do something reasonable, which is neat. Right, so you see, if we just look at nearest neighbors in this Jacobian vector space, then we get very sensible results like military is close to civilian, armies, commanders, infantry, Zen is close to Dharma, Buddhism, Buddha's meditation, and so on. And we can do this with things like movie ratings data too, right? It's not restricted to text. So the nearest neighbor for Casablanca is Citizen Kane. The nearest neighbor for Superman 2 is Superman 1. The nearest neighbors to The Princess Bride are movies that I grew up watching. So that's all nice. Another trick that we can do, because this is a nonlinear model, is we can come up with contextual word embeddings, right? So if instead of averaging over a bunch of different z vectors to get this Jacobian matrix, we just consider one z vector that corresponds to a particular document that includes some context. That context can actually disambiguate to some degree the meaning of this word in that context, right? So if you put a word like fires in the context of a word like burn, then you get the kind of words you would expect from that sense of the word fires, like ignition, combustion, engines, fuel, and so on. Whereas, actually that's not as simple as I thought. Let's look at bank and river. That was the bad example, sorry. That was the lemon-picked example, not the cherry-picked example. I didn't come up with that analogy. So yeah, bank and river gives you what you would expect, whereas bank and money gives you banking, government, bankers, comptroller, and so on. Okay, so we're really just sort of starting to look at this polysemy stuff, but I think it's an interesting direction. And it's something that nonlinear models give you a way of doing that is, you can also do with shallower models, but it's also straightforward with these deeper models. So to summarize, there's some issues with fitting these VAES to sparse, high-dimensional, heavy-tailed, text-like data, and we've addressed some of them. There may be room for further improvement, but we seem to have something that at least is working, which was sort of questionable before. We proposed a simple way to examine what it is that these deep models of text are learning. And if you want to talk more, I'll try and be at the poster a little bit later, maybe after the session. So with that, I'd be happy to take any questions. Thanks a lot.
So we have time for one question.
That's a nice talk. I really like this idea of using amortized inference to initialize the optimizer. There was some interesting work in EP by Nicholas Hess and Arthur Gretman and code that did something a bit similar, but they had an uncertainty estimate attached to the essentially the recognition model. So when the uncertainty was high, they could back off to doing the exact thing, and when the uncertainty estimate was low, they could just run with their amortized inference. I wonder whether you thought about doing something similar, and that could sort of alter how much you optimize, or whether you bothered optimizing at all.
No, I had not thought of that, but I should have. It's a good idea. Yeah, because I didn't go into detail on this, but yeah, this additional sort of inner loop optimization is expensive, right? And there's a reason that we all got excited about this inference network stuff. Yeah, being able to sort of guess when that's not a price that you actually have to pay, yeah, that would be great. Thanks.
One more question? Okay, let's thank our speaker.
Thanks.
So next we have